usually think of math as a very abstract topic, something that is defined by set rules, something that is done on paper, something that is defined on paper and remains on paper. So, how do these plants that have grown around me have some sort of similar architecture? Where is the blueprint behind this?
Now, one of many answers to these questions are known as L systems or Lindemann systems. At their core, they consist of three things: the axiom, which is the origin point, rules that derive themselves, and then repetition of these rules over and over, which then creates a shape. And remember that we're going to do this symbolically right now and then visually later.
Each step replaces symbols using the same local rules.
Now
No
here's a
symbol
representation of a
knows
more
the whole
natural
shape.
looking
That's an important
fern.
principle.
You have to
Global structure
realize real
emerges from
systems aren't
local decision.
isolated. They face
Complexity
limits,
isn't
space,
added,
direction, competition. When you add
it
constraints or
accumulates.
small biases, the same rules produce variation. Same grammar, just different constraints.
Then comes the turtle bridge that converts
The big
syntax into
idea here is
geometry.
that L
For
systems
example,
show
this
that
is the
growth is
axiom, which is
computation,
the origin point,
and
and these are
structure
the
doesn't need
syntax.
design, just
F,
iteration
which
and
draws
constraint.
forward, plus or minus, which changes direction, and these are the position based. So, what this turtle bridge and what this demographic does is it converts symbols and syntax into geometry that repeats.
Now, with all the visualization I've shown you about L systems, you might notice something very eerie about them that you might not notice in actual plants or actual trees, is that they're very, very symmetrical. Now, why does this not happen in actual plants? The reason is that because there are a lot of other variables that are acting on these plants, such as shadows, such as sunlight and the distribution of sunlight and competitions between these plants. This is one of the reasons why these plants are not as symmetric as are shown in visualizations.
Realize now that real systems aren't isolated. They face limits of space, direction, competition. When you add constraints or small biases, the same rules produce variation. Same grammar, just different constraints. The big idea here is that L systems show that growth is computation and structure doesn't need design, just iteration and constraint.